Really happy to have Grayson Buckingham and John Lee from DISA Technology. DISA specializes in a process called high pressure slurry ablation, which can be used for optimizing mining efficiency, cleaning up mining sites, and a number of other useful applications. But John and Grayson are both co-founders, and John, Grayson, maybe we can just hand it off to you.
Excellent. Yeah, thank you, Matt. And yeah, thanks, Matt and Eric, for having us on. My name is Grayson Buckingham, President and CEO of DISA Technologies. Started the company back in 2018. It's been a fun journey where, it's just a concept and a couple of patents. And now we've added to our patent portfolio significantly and have started to scale the technology up where we have several commercial installations. And I'll kind of get more into the problem that we're seeking to solve, but I'll hand it over to my co-founder, John Lee, to introduce himself.
Yeah, hi everybody. Thanks for having us. John Lee here, like Grayson said, co-founded the company together January 2018. So originally from Wyoming, attended University of Wyoming. That's actually where Grayson and I met. So our entrepreneurial journey kind of goes way back to our days during our master's degree. We kind of always knew we wanted to start a company, and just funny how life works. We were kind of encountered this opportunity and decided to pursue it full time. So launched this in January 2018. And like Grayson said, first day, it was just the two of us in the concept, and have now grown the technology to larger commercial size units and grown our team from us two original to 25 people today. So looking forward to diving in.
But the name of the company, DISA, is short for disassociation. And what we do is disassociate composite material into its discrete subfractions. So in layman's terms, we make it easier to separate valuable minerals from the waste material. And we do that through a technology that we call high pressure slurry ablation. The technology is applicable in mineral processing and for the remediation of uranium mines for the purpose of this presentation. And our main passion is for helping to clean up the 15,000 abandoned uranium mines that are scattered throughout the Western United States. So, as I mentioned, right now, the US EPA estimates that there's approximately 15,000 of these abandoned uranium mines, primarily in the Four Corners region in Wyoming, and really throughout the Western US. 75% of these sites are located on federal and tribal lands. The other quarter are on private lands. And in the West, approximately 1 in 5 people live within 50 miles of an abandoned uranium mine. And the issue on all these mines primarily were mined during the Cold War. Then the Atomic Energy Commission was largely responsible for purchasing and advancing the development of or the mining of these different sites. And there wasn't really a lot of oversight on these sites really until 1978 with the passage of UMTRCA, and then later EPA regulations came about in the early 1980s. And so what had happened is a lot of folks would go after mom and pop shops would start mining operations. They would try to take the high grade ore, transport it all the way to a mill, which would then be converted into U3O8. But what would happen is the low grade ore that wasn't economic at the time, they just left on the surface. Then we didn't really have a great understanding of what that meant. And so a lot of folks thought that it was benign to leave that material on the surface. But over the decades, as that material has sat really since the Cold War, it oxidizes, the uranium and radium leach into the waterways, and then those dust particles will blow into population centers to where today we've started to determine that there's a lot of negative environmental and health impacts to nearby communities by allowing these waste piles to continue to sit on the surface for decades to come. And so this is an example of a waste rock pile, not to be confused with mill tailings. This material has not ever been processed or treated. It's just been dug up from the ground and left on the surface. So this is an example right here of a site in Western Colorado that was the first site that we really started diving into and testing the effectiveness of our technology. That site's been sitting there since the 1970s. And even when uranium prices were at $130 a pound, it still wasn't economic to transport that entire material, all that material to a mill to be converted to U3O8. And without a large federal mandate to clean these sites up, it'll continue to sit there, indefinitely. And so this is a company called Cultiva that we've worked with. They measure land degradation over time. And basically what this chart shows is that's for that October pile in that prior slide, that over the decades, the more that site continues to sit, the more degraded that land becomes over time. And so we need to start taking action to address these legacy sites and these sins of the past that were largely promulgated by the federal government under the Atomic Energy Commission. just looking at the overall market view of these different sites. So, specifically for the defense-related uranium mines, there were over 4,200 of those legacy defense sites that were mined. And then the other 15,000 associated with uranium that produced during that time approximately 75.9 million tons of ore. Many of these sites are remote, and only, as I mentioned prior, the highest grades were shipped off due to high shipping costs, and then the lower, meaning the lower grade ore was stockpiled on site. So we've collected a lot of data. We worked with this company, WWC Engineering, to do an assessment of these different sites, and looking primarily at the four corner regions. They determined that the maximum grades are about 0.15% uranium and 0.6% vanadium. So relatively very low grades. But as I had mentioned, it's that long-term exposure where these health consequences can start to be more largely felt. And ultimately, the average grades on these sites that was averaged by WWC, it's about 0.05% uranium and 0.1% vanadium. And so a ratio that's used to estimate the amount of waste rock that was left on site versus the amount of ore that was sent to a mill, the common ratio is 6.451. So extrapolating that translates to approximately almost 500 million tons of waste rock at these Western U.S. mine sites. And so there's the potential at those grades to have 500 million pounds of U3O8 and 900 million pounds of V2O5 sitting in those waste rock piles. And to put that into perspective, the globe consumed just over 100 million pounds of uranium last year. So there's a significant amount of uranium and vanadium that continues to sit in these waste rock piles today. And so right now, the current condition is to do nothing. The only two solutions that have been used in the past and until our technology was recently validated by US EPA is to certain severe sites to bury all that material off site, which doesn't solve the problem. The contaminants are still there. Those enhanced capping barriers can still erode over time, and that material can ultimately, with the erosion of that cap, could still leach into waterways. And so, for in particular on the Navajo Nation, the nearby communities have significant concern about capping that material because the contaminants are still located on that site. And then the second alternative is to take all that material and haul it off site. Well, as we just saw on the prior slide, there's 500 million tons of waste rock, potentially significantly more. It's just cost prohibitive to truck all that material off site and then to dispose of it. And we don't even have the disposal capacity in the United States to be able to handle that volume of material. So that's where we come into play, where we're a waste minimization technology. I'll get into more detail about a treatability study that was sponsored by US EPA and Navajo Nation EPA back in 2022. But at present, we're the only validated treatment technology for abandoned uranium mine material, in particular in the Navajo Nation, where we can take all that volume of material, treat it through our system, and we effectively have two different streams. 80% of that material is typically clean enough to be left on site. And then you've got 20% of the overall volume that captures over 90% of the constituents of concern, which includes the uranium and radium-226, that can be either recycled or taken to a low-level waste facility. So I'll hand it off to John to explain exactly how the technology works.
Yeah, so hi, everybody. So the technology is called high pressure slurry ablation, HPSA for short. We call the technology HPSA technology. Essentially, what we're doing is taking this waste rock, mixing it with water to form a slurry, and then processing that slurry through opposing nozzles. So you can see there in the images, it's two nozzles pointed right at each other. The particles come together and collide and essentially form a particle-to-particle collision. This is important because we're using the particles themselves to break each other apart. Typically in the Western United States, the mineralogy we see is a kind of a quartz or a sand grain as kind of that base mineral with carnotite or other types of uranium minerals stuck to the surface of the sand grain. So this is kind of illustrated here with yellow. The yellow is the sand grain, and this is called mineral liberation analysis, where the uranium and vanadium in the form of carnotite or coffinite or whatever type of mineralogy is kind of stuck to that surface. It's important to know that it's stuck to the surface because then we can have a clean liberation with our technology. So HPSA is essentially a selective liberation technology where we can take the technology right to the site without any chemicals, simply mechanically process this material and have a selective liberation where then we can concentrate and remove that uranium, vanadium, radium-226 in the fine fraction and leave a clean, coarse sand product behind. So this is essentially where we're able to come to the site, pre-process this material and then remove just that target mineral rather than removing the entire mass of the site. And as you can imagine, this plays into the economics then, where you don't have to transport 100% of the material, but rather a concentrated fraction, roughly 20% of the overall mass.
So diving into our treatability study that was sponsored by US EPA in 2022, we went down to 3 sites on the Navajo Nation. And the US EPA and Navajo EPA were asking 3 main questions. How effective is the technology? How economic is it? And then does it work on a wide variety of material? In terms of how effective, we're looking at 2 main things. One is toxicity, our ability to reduce toxicity, and the second is leachability. So for toxicity, we were able to remove up to 98% of the uranium. And for leachability, on all samples that we tested, we eliminated leachability concerns and brought everything below the water quality standard. And then in terms of economics, compared to hauling all the material off site, we were estimated to be 50 to 80% more economic than that option. And then we were able to successfully address those questions on all 3 sites where we tested the material. So these are just some snapshots of select samples that we tested at those 3 different sites. So the starting amount, this is at the Old Church Rock mine. You can see there's 940 parts per million uranium in this particular sample and 228 picocuries per gram. After we run that through our system, we bring those levels down to 17 parts per million uranium and 18 picocuries per gram radium-226. And that is just in the fines are in 23.5% of the overall mass. So what that means in that percent mass to concentrate is instead of now having to haul 100% of that material offsite, you now only need to haul 23% of that material offsite, and then the remaining 80% can stay on site as that clean and stable fraction, depending on cleanup goal standards. And this just shows what our recovery rates were of the uranium and radium-226. So significant. And then what this chart below shows is that leachability question. So the feed leachability is how that material sits currently. And right now it's at 0.23 milligrams per liter of uranium and 25.4 picocuries per liter of radium-226. So the water quality standard is this bottom row. You can see it's significantly above what the water quality standard is. But after treating it through our system, what this row, the HIPSA leachability demonstrates is that we were able to bring the leachability results actually to non-detectable levels, so below that water quality standard. And then the radium-226, we were also able to bring below that water quality standard. So now that with this site, there's no longer a threat of leachability for that nearby community and for those sites cleanup goals. And then the Quivira Church Rock is another massive abandoned uranium mine. It's over 1 million cubic yards. And I'll kind of walk everyone through on what those different options look like in the following slides, but similar results where we were recovering 96% of the uranium, 94.6% of the radium-226. And again, and the HIPSA leachability, bringing that well below the water quality standard, where at how it sits presently is significantly above that water quality standard. So, this was taken directly from an EPA report, but these just show the key findings of that treatability study, which allows us to state that we're the only currently validated treatment technology for abandoned uranium mines. But their key finding, our technology was able to achieve greater than 90% reduction in uranium and radium-226 concentrations. The treated quartz fraction does not leach metals or radionuclides. And then we have different operating parameters that John was walking through our technology that can be deployed to be able to meet different cleanup goals. So we can process material longer, if you want to get lower goals, or, if we're trying to achieve higher throughput, it's really just a matter of what our different velocities are, what our percent solids are, and the amount of collisions that need to be achieved to hit those cleanup goal standards. And so the treated fines fraction requiring offsite disposal is as low as 17% of the original waste volume, providing up to an 83% reduction of the original waste volume. And just, to know how important that is, it's a key tenet of CIRCLA to engage in waste minimization when cleaning up Superfund sites. And one question we get asked a lot about is the water that we use in our system, because we do use water as a medium to transport the solids. It is recycled throughout our system entirely. We do lose a little bit of water in that dewatering process, which is the final step in our circuit, but it's about 10 to 15% moisture, which is what would be required anyhow for the compaction of dust for that site. So, ultimately the water is a marginal cost, and at full commercial scale, running 100 ton per hour units, you would only need a few water trucks a day to resupply that water. And then, again, as we mentioned, significant cost savings of 60 to 70%. So this is an image that we put together, estimating that Quivira mine site. So this is how that cap, sits now, over 1 million cubic yards. This would be the option of transporting all the material off site. On average concentration grades for this particular site is 400 parts per million uranium. And there's over 1 million pounds of uranium located here, and the radium activity quite high at 121 picocuries per gram. Each truck located here represents 450 trailer loads at 16.7 cubic yards each. So, 60,000 trailers would be needed if it was ultimately decided that all this material is going to be hauled off site. So not only is that significantly expensive, but it's also a major impact to the local community with truck traffic going back and forth. I think I saw one report that estimated over 13 years of trailers going back and forth to dispose of just this one site. And on the Navajo Nation, there's 523 of these abandoned uranium mines. So the other option being contemplated is to cap all the material in place. Here, we estimated a 3-foot cap that would be used. So 65,000 cubic yards of cap material would be required to be brought on site for the capping. And here you would still need 3,900 trailer loads to just cap that material. And the major issue with this option is that uranium and that radium-226 still remains on site. And that material is potentially leachable, especially if that cap erodes over time and there's disturbances there, so which would exceed water quality standards. So you're not solving the problem, you're just bearing the problem, and it's still going to be there throughout time. So what our option looks like here is the HIPSA treatment. So assuming that we're reducing the volume that would need to be taken off by 80%. So this is a 20% of the fines that would need to be recycled. You can still see there will be trailers needed loads to move that material off site. But we're getting over that 90% recovery, and so there's 1 million pounds of uranium, which even has the potential to be recycled and put to productive use, and which could even help further reduce the overall project cost for this. And then now this pile, you would still have 781,000 cubic yards that could be cleaned and reused, depending on the land use levels, where we've brought the average radium activity in this example below 8 picocuries per gram, which achieves that open land use limit. And then the material leachability has been reduced to below those detection limits, so there's no longer that threat. And then we also have, if there were certain cleanup goals, the ability to retreat that material and potentially reduce uranium concentrations to as low as 2 parts per million uranium and 1 picocurie per gram radium-226. And then I'll just kind of hit on one more slide. In a separate study, Idaho National Labs also came to our facility a few years ago to verify our results. This was on a site out of Colorado on the Paradox Valley material. And then overall, they concluded that the tests indicate our process appears to significantly liberate and separate the softer valuable metals into the fines fraction without needing to fully size reduce all the material. And with that, I'll hand it back over to my colleague to talk about the status of our technology.
Yeah, so kind of like I said in the introduction, when we started the company in January 2018, we had one small kind of laboratory size unit. So most recently, we've really kind of grown our team and started to scale the technology from an engineering perspective. So a lot of people have commented like, hey, it's great that it works in the lab. What does it look like at scale? So this past year in 2023, we built what we call Gen Bravo. Gen Bravo is just the name of kind of the concept of the technology as it continues to scale. That technology there is for 5 tons per hour. As Grayson kind of mentioned in the beginning, not only does it work on remediation of abandoned uranium mine waste rock, but also traditional minerals processing. So that unit's at a phosphate mine right now, processing continuously at 5 tons per hour. It is a platform technology, so it can work on a variety of different minerals processing applications, but also the same technology is applied to the abandoned uranium mines. So kind of validating that scale at another application. The Gen Charlie 3.5 ton per hour unit, we just built that this year, 2024. That's going to a graphite plant up in Eastern Canada in the next week. And then this Gen Charlie 20 ton per hour, that's a unit we've engineered, and we're kind of finishing building that and shaking it down. That would ultimately be the unit that is deployed as the next scale to an actual abandoned uranium mine. So in the prior treatability study with US EPA, we did more of our kind of batch process pilot plant, and now we're gearing up to do a 20 ton per hour commercial phase 2, if you will. And that's kind of illustrated in that third picture there. And then finally on the right, continuing to scale the technology just to larger and larger scales. As you can imagine, with larger scale, more throughput, the better the economics look. So that 50 ton per hour Gen Charlie unit will be going to the phosphate mill to validate that concept of the technology works later this year. And this year kind of just shows an additional kind of picture of that 10 to 20 ton per hour unit I was talking about going to an abandoned uranium mine. This is representative of what it would look like if it went to an abandoned uranium mine. So kind of in the upper right corner, you can see some conveyors, some screens. We would kind of take that material as it sits as waste rock. There might be larger particles. Those particles or rocks might need to be pre-screened out. And then the material is fed into the DISA system, mixed with water to form that slurry. And then ultimately it goes through where Grayson's mouse is, that high pressure slurry ablation, or the DISA portion of the process where that liberation and particle collisions take place. After we've liberated the uranium, vanadium, and other constituents of concern, we then screen the material on the backside. Again, that uranium and vanadium and radium, they all settle into what we call the fine mesh fraction, but essentially the very, very fine material. So we're just separating it based off size with simple screens. And then the coarse material, the larger material, is the clean sand that ultimately then goes back on the site as that safe and stable fraction.
Yeah, so with that, we'll kind of conclude the overall of our technology presentation, but in some, we're really passionate about at DISA is, how can we start, advocating for a nuclear renaissance when there's still many legacy sins of the past, and we need to get this cleaned up. And what we're really excited about is that we have a solution to do so in a way that's economic, that's sustainable, in a lot of ways doesn't even require taxpayer dollars, because we're able to recycle the material to help pay for our remediation activities. And furthermore, when we're a country that imported over 47% of our uranium from places like Kazakhstan, we can help offset bringing in sources of uranium from places of the world that aren't as friendly, like with the recent ban on Russian uranium. And we have those resources here in the United States, and we can do so in a way that remediates these legacy sites that have been out there since the Cold War, and helps foster this nuclear renaissance. I know everybody here on this call is very excited that that's starting to occur. Yeah, thank you. Thank you for hosting us.
Thanks.